So that's one option. Or option number 2, start the exact same way. Determine the number of half-lives, right? And then for those of you who are like, this mathity math looking thing right here, not okay with it. Okay? Then somewhere on your paper, draw the following picture. Now, if we use that graph, we know 2 half-lives have passed because we calculated it. 2 half-lives, trace it to find where it crosses the line, right? Read the graph for it, we end up with a quarter. I don't have a preference for which style of solving you use. If you are like, I can memorize that graph and write it down, then memorize the graph, write it down, and then when you solve the problems, simply say, read the graph for, and you only have to draw the graph once. So if you have 3 problems that use that one graph, just draw it once and then refer to the same graph. Make sense? Next one. This one is slightly trickier because they don't give us years. They do give us the remaining amount of radioactive atoms, and they give us the amount of product that has been made. So they give us the amount left and the product. What do I have to do with the amount left and the product to find the total amount that I started with? God bless you. So at time 0, I had 500 radioactive atoms. Do we all agree? Okay. If I currently have 125, that tells me the percent I have that remains, right? What is that number? 25%? Yep.
Are we going to the number of half-lives still?
Mm-hmm. Now you're like, but wait, now all I know is 25%. There's more steps, right? So, 2 choices again. Choice number 1. Now this is going to require you because, again, God bless you. Again, we don't necessarily know how to solve for x, right? I can't just put 0.25 here and solve for x because some of us have gotten there in our math classes and some of us have not. But what I do know that you're capable of, convert 0.25 into a fraction. Fractions are our friends here. Make it a fraction. What would that be?
1/4.
So I know that this is equal to 1/4. Are you able to determine 2 to the x equals 4, what x would be? That's a simple one, right? You're like, psh, easy. Okay. 2 to the x equals 4, what is x? So 2 half-lives have passed. Again, our other choice. Read the graph for where it says 25%, right? Read it for where it says 1/4. we find out that corresponds to 2 half-lives. Answer is 2 half-lives. Either way, we arrive at the same answer, right? This part for us can be a little bit tricky if we aren't good at converting our decimals back into a fraction. So let's take a look at the ones that you need to know. 100% as a decimal equals what? As a fraction? Right? 50% as a decimal? As a fraction. 25% as a decimal. And as a fraction, we already said it's quarter. And 12.5% as a decimal. And as a fraction.
1/8.
And then 6 1/4 as a decimal. And as a fraction. Last one we'll do. We're not going to go past this number, right? 3.125% as a decimal.
0.02125.
And as a fraction. So if this is 1/2 to the x, what is the x here to get 1/1? 2 to the x equals 1. What is x?
0.
To get 2, what is x?
1.
To get 4, what is x?
2.
To get 8, what is x? This is where I found most people made mistakes yesterday. They desperately just wanted to put 2 to the 2 to get 8. Or 2 to the 4 to get 8. 2 to the 4th isn't 8, right? 2 to the 4th is 16. And then, so these correspond to your half-lives, right? This is the fraction remaining. This is the percent remaining. Do you have to memorize those? What do you think? You have to memorize this whole piece of paper? Or piece of paper? If you know that, you know everything on the previous screen. Think you can reverse engineer it from there? You guys are like, no. Okay. If you know how to fill that out, you know everything on the previous screen. Pick your poison, friends. I don't care which one you memorize. Whatever one you learn, whatever one you're comfortable with, you can accomplish the same thing from both. Are we comfortable that we have at least one way to solve these problems?
Yes.
Okay. This is usually one of those things that we get stuck on, that we remember even into our junior year how hard we thought it was freshman year. So I just want to make sure before I move on from it, we're all like, it's a little weird, it's a little, I'm not sure yet, but I'm okay. But you guys were pretty fast yesterday, so just want to check. Okay. I'm going to distribute one of these to all of you. We can affectionately consider this the anatomy of the periodic table. All its basic parts. And if we learn all of its basic parts, then we can understand why the things on the periodic table do what they do and how they behave. So you've been answering questions in your bell work all week about chemical reactions and polar bonds and all these things, and we haven't gotten to how the periodic table works, which is why some of those questions were probably just look it up and we don't understand it. First thing I want you to do is draw the following line, any color, it can be a darker color, draw the following line. It's a nice little stair step. Nice little stair step. Does this stair step cut the periodic table in half? Not even remotely close to half, right? What fraction would you give it?
1/5.
You guys are like a fifth, an eighth, fourth, a third, third and 2/3. 2/3 on the left, a third on the right. I should tell you, these two rows down at the bottom, they do this like nasty little trick. They actually insert right here. You'll notice that it goes out of order numerically right there. Goes 57, 72. Well, that's because 58 through 71 fit in there. But it would make it so wide, it would never fit on the page. So they call this the abbreviated periodic table. Most periodic tables will show you that. You can just kind of like put a little arrow in. These guys down here, you don't necessarily need to know their names, but they're called the lanthanides and actinides. And we put them down there just so we can shrink up the periodic table, make it a little more narrow, and fit it on the page. The vast majority of the chemistry you will do in high school completely ignores these two rows. Don't you feel bad for them now? They get edited out. They get put down at the bottom. Everybody ignores them. They're radioactive, so nobody wants to play with them anyway. I mean, they likely have a complex. And besides the fact, only one of them, I do believe, yeah, there's one of them that you have to learn the name of. And the rest of them, they really do get ignored. I mean, it's dreadfully sad. So poor lanthanides and actinides, no fun to be them. The line you drew with that nice dark line divides our periodic table into metals and nonmetals. See if you and your partner can determine which side are metals and which side are nonmetals. What side is which? Left side's metals, right side's nonmetals? So you're telling me potassium is a metal? Sodium? Barium? Okay. The only one on the left side of the periodic table who is an exception to the rule is hydrogen. Oh, the rebel hydrogen. So go ahead and color all of the metals on the left side of the table, except don't color hydrogen. Color them one color and label them metal. And then, when you're done with that side of the stair-step line, go to the other side of the stair-step line and color in your nonmetals. Now that we have our metals, nonmetals, noble gases, and metalloids, I'm going to flip to a clean periodic table, but you guys can keep writing on the one you're writing on. number the columns on the periodic table. But we're going to number it in a way that is not the way that the vast majority of the chemistry books that you see are going to label it. Yep? You can if you want, the metalloids, yeah. So here's the thing. The way I am going to teach you to label these columns is what we call the American system. The American system is not what we currently use. We use the International Union of Pure and Applied Chemists system, the IUPAC system. But the IUPAC system makes it harder to learn some of what we have to learn. So, you know, I do go metric system with IUPAC on everything else, and I forsake the English system. But this time I'm going to embrace the American system and tell you to label this first column with a 1, a 2, skip 3, 4, 5, 6, 7, 8. So we go ahead and label our columns 1 through 8, skipping that middle section. That middle section, in the American system, we call them the B group. And we label them with a different set of letters and numbers. So we've just labeled the A group. In the A group, for the purposes of biology, all you need. You don't need the B's. Now, the reason I had you label these is because it tells us something very important about every single atom in that particular column. And the numbers that we've written on the top of the column actually correspond to the number of electrons on the last shelf. Except we don't actually call them shelves in chemistry, we call them shells. So that number at the top is the number of electrons in the outermost shell. So the farthest away from the nucleus, it's the number of electrons. Everybody in column 1 has 1 electron in their outermost shell, farthest away from the nucleus. Everybody in column 2 has 2. Everybody in column 3 has 3. Everybody in column 4 has 4. Everyone in 5 has 5. Everybody in 6 has 6. Everybody in 7 has 7. And everybody in 8 has 8. I know, you're like, wow, that's kind of like numerical order. Not only is it kind of like numerical order, it's actually numerical order. The American system would have you label those 1 through 18, and then it would not work out. Not the American system, the IUPAC system. That's why we stuck with American. Super easy. Now here's the secret about atoms. You know how I said they wanted full shelves? You know the only column on the periodic table that has a full shelf? The noble gases. The noble gases. 8 is ideal. We call it an octet. Any atom that undergoes a chemical reaction does so to complete its last shell, to make sure it has 8 electrons. Everybody's going to do that. We call it the octet rule, or completing our valence shell. Valence just means outermost energy level. So they're all going to work to complete their valence shell, the outermost electrons. Noble gases, another name for the noble gases is inert, I-N-E-R-T. Why? It means non-reactive. If your shell is already full, you're not going to do anything. There's a reason we call them noble gases. When was the last time you actually saw nobility do something useful? Exactly. You're like, well, I've never seen nobility before. Listen, Harry and Wills, they do nothing. Right? They smile for some photo ops. Don't even talk about Harry. Harry is like helium. You notice helium hanging out at the top of the periodic table? It's like the delinquent of the noble gases. Secret? Doesn't have 8 valence electrons, it has 2. And it's totally happy like that. Harry, he doesn't follow the rules, right? I mean, Vegas, we all saw that in the news. You see that? Mm-hmm. Prince Harry went to Vegas and got himself in a spot of trouble. And you know how they say what happens in Vegas stays in Vegas? Not if you're Prince Harry. So, helium, that's Harry. Wills, well, Wills is something like argon or krypton. Nice, reliable, well-behaved, always smiles for the photo op. Noble gases never do anything. Like Harry, like Wills. They marry other nobility who will also do nothing. Life is good doing nothing. It's everybody else in the periodic table we got to worry about how they're going to fill their shell. If you have a bookshelf that has 1 book on it, and your bookshelf holds 8 books, is it easier to just figure out how to donate 1 book to the Goodwill, or go buy 7 more books? Yeah, go donate the book to the Goodwill, right? You're like, yeah, it's a lot easier to get rid of 1 thing than find 7 more. But if you have 7 books, you can go find 1 more book to fill that shelf, right? Same thing's going to happen on the periodic table. Whether you have 1 or 2 or 3, if you have 1 or 2 or 3 electrons in your outermost shell, it's way easier for you to give those electrons away and just be like, you know what, you take these, I don't need them. So then you go back to the next shelf, right? That's full. Makes sense if you think about it like your bookshelf, right? If you have 5, 6, or 7 books on your last bookshelf, you're simply going to get the number you need to get to 8. Where do you get them from? Well, those people on the other side of the table who are like, take these off my hands, I don't want them. That was it. Proton, 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 neutron, neutron, neutron. Okay, I have the nucleus of an atom. Now, this is just going to be a hypothetical atom. Don't sweat it too much. Really? That's kind of awkward. So, when you have electrons in an atom, they have to get stored in the electron cloud, right? We said that's where they go? I think maybe it was this hour, maybe not. We might have talked about how to put books on a bookshelf in here. Did we talk about that in this class?
No.
Okay. So this is a matter of simple physics. If you are going to load a bookshelf, you went to IKEA, you bought a bookshelf, you spent 2 hours not cursing or using profanity in assembling the bookshelf, because you would never do that. But you assembled the bookshelf, and now you're like, sweet, I can put my books on it. Oh wait, you don't have books, you have iPads. Where would you start putting books on the bookshelf? Simple physics tells us where to start.
The bottom.
Why the bottom?
It could become too top heavy if you put like the heavy stuff on the top.
It's too top heavy. There's actually one of the IKEA sets that's currently being recalled because it's toppled over on toddlers. Because the way that it cantilevers, if you load it, it just... So we understand the physics of it. If you put something on the top shelf, has a lot of potential energy, right? The higher off the ground you are, the more energy that it's going to, potential energy that's going to have. Potential energy converts into kinetic energy. Physics, yeah? Don't tell Mr. Nanini that's my description. He'll be like, I'm pretty sure it's not a physics term. In biology it is.
Very technical.
Yeah, absolutely. Coefficient of friction and everything. So we know we start at the bottom and work our way up. In any atom, same story. If we have electrons that have to get stored, we are going to start at the place with the lowest amount of energy. It turns out the place with the lowest amount of energy is closest to the nucleus. But once you fill that shelf on the bookshelf, the bottom shelf, once you fill it, where do you go?
The next one up.
Next one up. And we just keep on going, right? Same thing in any atom. So if we have 2 electrons to place, we're going to put them right here on the bottom shelf, closest to the nucleus. Now keep in mind this does rely on that icky Bohr model where we have like that orbiting nonsense. We know that's not an accurate picture, but it's the best for the description. Once we filled that, we move on to the next shelf, and the next shelf, and the next shelf, until all of the electrons that we have a place to live. We all okay with this idea? And energy increases as we move farther away from the nucleus. Much like our bookshelf, it is better to have lower energy. You want to be in that lower energy, it's more stable, life is good. And then, strangely enough, this is just for my own feng shui, some of you may agree, some of you may not. It is irritating to have slightly filled bookshelves, right? You're like, no. You finish filling the shelf. Even if you have to put like a bookend and then some like decorative tchotch on the shelf. You put something on the shelf, agreed? Okay, atoms, gonna do the same thing. They want their shelves to be completely full. The last one they put an electron on, they're going to fill that shelf. So we can go back to our periodic table. That process is how we go from being an atom to an ion. So we go from being neutral with the number of electrons, protons, and neutrons that we came with to being charged. And you're charged because you've decided to either take electrons to complete your octet or to get rid of electrons to complete your octet. And if you get rid of a negative particle, and you used to have an even number of positives to negatives, you get rid of a negative, what are you?
Positive.
You're positive. And if you take more negatives on, what are you? So there's a way to remember this. We need that periodic table. At this point, you can just doodle all over your periodic table. That's what I would do. So we have our line, yada, yada, blah, blah, blah. This was 1, 2, 3, 4, 5, 6, 7, 8. If you have 1, 2, or 3, you're going to chuck electrons, right? Easier to get rid of that number than it is to gain. So you are going to be, if you get rid of things, what are you going to be? You're a donor, which makes you what charge?
Positive.
Makes you positive. Here's a way to remember it. If you can remember 1, 2, and 3, and you remember the idea that getting rid of 3 things is easier than gaining 5, then I want you to think of Santa Claus. He's a giving guy, right? Flies around the world, gives stuff away. All in all, I'd like to be his friend because he seems fairly positive. Would you say he has a positive disposition? So anybody on this side of the table, they're going to become positive when they form an ion. Santa's counterpart, who lives on Mount Crumpet, right, yeah, Mount Crumpet, yeah, sounds right, whose heart is 2 sizes too small. He has breath like onions, and I'm pretty sure he once stole Christmas. Stole it, right? Took it from all those poor Who's down in Whoville. You want to be his friend? This is always where there's one student who's like, yeah. Yeah, let me know how that works for you. Who is that guy? The Grinch. And would you say that overall he's kind of a negative personality? Negative disposition. He did get, well, spoiler alert, he got nice at the end. I know. Ruined the movie.
I was halfway through the book.
It's a long one. My nephew made me read it to him in July because he didn't want me to leave. He's like, you can leave after you read me a book. And then he went to his room and found the longest book he could. And I was like, seriously? That was intentional.
He became good when he gave all the gifts back to the
He did become good when he gave all the gifts back. And then what happened? They shared. Ugh. That's
If he
covalent
took the
bonding.
gifts and then gave them back when he was being killed.
He would be, but they invited him to Christmas, right? So they got to actually like stay and bond over. Oh. Bonded over Christmas. I know. I always teach this unit in October, and then I'm like, we're talking about Christmas. It's all good. So the Grinch is fairly negative. If you are negative, you take. You're negative. The number, well, you may notice if you give away one thing, you're going to have a charge of +1. If you give away 2 things, you're going to have a charge of +2. If you give away 3 things, you're going to have a charge of +3. If you have 4, you're not going to give or take because you have the perfect even number. You would rather share, so we just kind of skip you. You're sharers. Well, not those guys. They're not sharers. They're givers. But here's where we start being takers, at number 5. How many things do you need to get to 8 if you have 5? How many are you short?
3.
So you're short 3, so -3? That's what your charge would be. And if you have 6, how many are you short? So you're -2. And if you have 7, how many are you short? A -1. So not only does the American system tell us how many electrons we have in our outermost shell, it tells us what our charge would be if we were ions. Now there are funny names for these positive and negative ions. If you are a positive ion, you are a cation. I did not make that up. That is actually what we call them. I know. You're like, that sounds like something she'd make up. I agree. It does sound like something I would make up, but I didn't. So if you are positive, you are a cation. And if you are negative, you're an anion. Metals form cations. Metals are givers. Metals are positive. Non-metals are anions. They're negative and they're takers. I just insert this foot back in. Yep. Right there. There we go. We got it.
They should change the name to cat ion and dog ion.
It would be convenient. I did have a student, however, once draw an ant for anion out of all negative signs, but then they called it antion for the rest of the semester. I was like, it's not an antion, it's just an anion. It's an ion. It also reminds me of onion. Onions are negative. Nobody would just like eat a raw onion.
My brother did that before.
Ugh. I'm not going to ask. So, cation, anion, are we comfortable with the idea of why we would gain, why we would lose? Like, kind of, sort of, we're like, we get the idea that we want everything to be like full and even. Your bookshelf's way less likely to topple over on you. Fewer toddlers get crushed if you have full shelves. We all agree that crushing toddlers is like bad. Usually. Quite typically. That was cold.
What did he say?
I said we all agree. Oh, and it's for him. That's even better. I said we all agree that crushing toddlers is bad, and he said it depends on the toddler.
No, it's always bad.
See?
That is always bad.